This is the Ambar Podcast. Released February 17th, 2019. Episode 430. Shahriar discusses 5G.
Welcome to the Amp Hour. I'm Dave Jones from the EEV blog.
And this is Shahriar from Nokia Bell Labs and the Signal Path.
Shahriar, how you doing?
Good. How are you?
Awesome. It's just us. Chris has bailed today.
I know. He's abandoned us.
It was just us last time, wasn't it?
No, he was there.
Oh, was he? Okay.
Yeah, he was. Yeah. This is the second time that I have had the pleasure of being on this podcast. I'm looking forward to it.
I thought it was the third. I thought we've had you on twice.
No, I only had it once before. It's actually been quite a few years. It's got to be, I don't know how many years it's been, but there's a lot has happened to everything in the past couple of years.
Including your intro, because you used to be just Bell Labs. Now it's Nokia Bell Labs. Tell us about that.
Yeah, so obviously Bell Labs has a long history. It used to be part of Lucent, and then Alcatel-Lucent, and then eventually Nokia purchased Alcatel-Lucent and Bell Labs, which comes part of that. So now we are the research consortium of Nokia. And we've grown in many ways because researchers from Nokia Labs have also joined in. So now we are even a bigger research entity. I think in the world, we must be at least in the top 10, if not even better, in terms of the amount of dollars spent for pure research every year. So it's quite nice to work there.
Fantastic. How many people came over from, like a split in terms of number of research people between the two?
Oh, that'd be hard. I don't think I would know exactly how many, but certainly grown maybe about 20% or so. I'm not sure exactly.
Right.
But it's been there's a lot of good researchers obviously at Nokia too. So joining Bell Labs is a natural thing for them. What
sort of research did they do? Was it in the similar sort? Because you're into like the the bleeding edge, high frequency RF, silicon stuff.
Yeah. So the department that I run at Bell Labs is the millimeter wave ASIC research department. So we focus basically on the integrated circuits for very high frequency and interesting applications, both for optics and for wireless. But Bell Labs as a whole has research across pretty much every domain you can imagine, from quantum computing to software and AI and hardware and applied mathematics and optics and you name it.
Wow, I had no idea.
We have also an interesting, it's a reasonably small department, but they do quantum computing and some interesting architectures and how they're pursuing it. Very cool stuff. That's one of the reasons I really like Bell Labs is because you can walk down the hallway and talk to experts in almost any field you can imagine. And that's very common in the world. Yeah.
I can imagine the lunchtime table. If you just go sit down at a random table at lunchtime, like what would you...
I know. One day, exactly. One day you could be talking quantum. The next day it would be AI. You never know.
That's fantastic. So are you all in the one big facility or are there multiple facilities?
So I work at Murray Hill campus, which is in New Providence. That's the original kind of Bell Labs in New Jersey. And there's a couple of hundred Bell Labs employees there and maybe thousands or so of Nokia. But Bell Labs is international. It's spread around the world, in Ireland, in the West Coast in the United States. There's all over the place. There are Germany and so on. And there's a lot of teams. They're all working in different things. But we're essentially in contact all the time and trying to collaborate.
Right. And how did it end up as an international thing? Did Bell Labs just buy companies and research companies in other countries and just kept them there and they became Bell Labs, or did they decide, well, we're going to start there for tax reasons, or for we've got good universities there? What's the...
Well, Alcatel-Lucent and Nokia, they're both international entities, and they have offices and headquarters and places all over the world. And as a result of that, some portion of those places become research, and that they become part of Bell Labs. Yeah.
Awesome. So your group, the millimeter wave group, what's focused on researching and producing? Is it practical silicon, or is it stuff that will go into a final product that you can buy?
Yeah, no, we do certainly have silicon in products, primarily in the backhaul point-to-point radio business, operating, from 6 gigahertz to 86 gigahertz. We have products in those domains. But a lot of the stuff that we work on, integrated circuits we work on, are generally targeted for potentially becoming a product in, let's say, 4 or 5 years or so. But we are researching. One of the interesting roles that Bell Labs has for Nokia is that we essentially de-risk a particular technology before Nokia would take it over and productize it. So we can figure out if a particular path of some particular design is worth pursuing by trying prototyping and investigating, and then we can feed that information back to the business units of Nokia and tell them, listen, don't do this, do that. And that can save them a huge amount of money, because as you know, to develop a product before you realize it's no good is not the best way. So that's one of the things we do. But in terms of integrated circuits, we do circuits for optics and circuits for wireless and, the 5G stuff that's people talking about. We investigate and explore those spaces quite a lot.
So would you hand over, would you go, right, we've done the research on this chip, we think it's practical, would you hand it over to a group who then turn it into a practical silicon? Or would you guys do the layout for the final chip as well that it's going to market?
Oh, no, we do everything to the end except for prototyping. Yeah, we built the silicon, test it, characterize it, and then, but at the same time, you can build something up to 90%. That 10% to get it, that's a lot of effort. So we call that the boring part. We pass it to the business.
Most engineers don't hate that last 10%.
I know. So we're spoiled, because once it gets to a point of being really serious for that kind of ambition, it just gets basically passed forward. Yeah. So then we can focus on something else.
I love it when you can just throw it over the wall and thank you very much. That's done and dusted.
I know. I wish it was as simple as that, but it's almost like that. Right. We just say, okay, you guys take care of it from here. But they're generally, they'd be quite happy if someone takes something to 90% and de-risks it. That's very valuable for the product unit.
Of course. So do you guys because you're involved in the silicon side of things, do you have your own little mini fab where you can fab your own silicon, or what's the deal?
So there are some indium phosphide 3.5 labs that we still have, and they make specialized optic components, but we don't make silicon integrated circuits from our own fab. That's just that wouldn't be practical, because it's almost impossible to compete with the state-of-the-art silicon foundry, whether it's silicon germanium or just CMOS or anything of the variants. We always send those out to those famous big fabs around the world. We send them to those. We design in their design kit, and then we submit it to them for fabrication.
Got it. So what sort of priority do they give you? Because they've got to produce, have they got lines that just produce prototype, short run silicons, or do you get them produced on the main production line, and you've got to slot in with other large the Apples and whatnots of the world?
Well, it's always an issue of money, right? So if you go to a foundry and say, here's X amount of money, you can always get them to do it faster. There's no question. And generally, these fabs always have something they call a bullet run or a high priority run, which can cost as much as 2 times or 3 times the mask cost normally, and then you get ahead of the line. Now, for us, we typically don't do that as often, because it's pretty expensive. But for research, it's a lot of these general high volume, high capacity silicon processes have what we call tape outs almost every month. So you have an opportunity to submit, and it may take 2 months, 3 months, depending on the foundry, for it to come back. But they're cranking this 24 hours continuously, right? Sure. So it's not that bad. Sometimes things get delayed, and you can have an unfortunate situation, and then things can get even further backlogged. And if you're at the edge, using the latest, greatest technology, which we tend to do, sometimes they're not fully production yet, and they're somewhat experimental from the foundry too, and that can also cause delay. But that's the price to pay if you want to use what's the best in the market.
Of course. But even if it's a couple of months, 2 or 3 months even, that gives you time to develop the test fixtures, develop and make all the test hardware and stuff like that, wouldn't it? So you're not just sitting around, twiddling your thumbs idle.
Oh yeah, for sure. There's always something to do. Yeah, absolutely. You get ready for testing and even working on the next tape out and the next chip cycle, there's always something going on. And there's not, my department is there's about, including myself, there's 8 of us, so it's not like a huge department.
No,
but
that's small.
yeah, they're all PhDs and they're all researchers, so they're constantly thinking about new problems and working on new projects. It's good. It's fast moving and very multidisciplinary, which is kind of unique.
How do you juggle multiple designs and products at the same time?
Not very well. It's tough. It's tough to do that, but at the same time, it's kind of fun because you're thinking at different planes. But normally, when it's really close to a fabrication of a project, and everyone's kind of thinking about that, and then once that tapes out, then you can maybe think about something else. But it's normally, this multitasking juggling is hard, and it is the nature of research in a way to think that way. So most people enjoy it who are there.
Okay, so in the research side of things, you're not always just focused on the one thing. Your mind's always darting around, is it?
Yeah, you have to, especially if you're working on, let's say, wireless circuits and optical circuits. And these are quite different in many ways. So if you're trying to, let's say, break a world record building a wireless system, and then at the same time, 6 months later or 4 months later, trying to do the same thing for optics, your mind has to go all over the place, back and forth. And like I said, there's not that many places in the world who have this kind of diversity of expertise and diversity of projects. But people who work, let's say, in our department get exposed to really different set of ideas and different set of skill sets. And that can build a really nice career for you in the long run, because you can pretty much go anywhere and you'll have expertise in that field.
For sure. So, but that comes it always comes at the price of when you're chopping and changing all the time, getting back up to speed.
Yeah,
because
when
you're hyper focused on the one thing, and that's you're doing that 24/7, then you're going to get really efficient at that. But then if you suddenly wander for a week onto something else, and then or worse, a month or something, and try and come back and come up to speed, is that a problem?
Yeah, that's why I try to often assign the people on the team where they have something that they are mostly present in, and they spend, let's say, 20% of their time on something else, or 30%. So someone kind of owns a fundamental project at its roots, so it doesn't get lost in the going back and forth. So people are owners of something, and then they contribute 30% of their time to something else, and that keeps a nice flow and ownership of a particular project, and people don't have to spend so much time and resources overhead jumping back and forth then.
Nice. Do you guys have a similar thing to Google in terms of, like, your free time or whatever? You can spend X number of hours a week just working on any, harebrained scheme you like?
Free times? I never heard of that such a thing. It doesn't exist. Normally, I mean, people in research tend to really love what they do. But I see people having all kind of interest. We don't have that explicitly, but a lot of people kind of do work with other teams, other places in the lab, sometimes in some whatever it is free time they can get. It's kind of like that, but it's not explicitly written as Google has defined it. No.
Sure. Well, it's different between. Well, I'm going to have 3 different aspects here: software, hardware, and then research. Leading edge research that you guys do, rather than just generic engineering. Hardware, I imagine, like in software, it's just easy to go off and just work on some little sub project for an hour, a couple of hours a week or something like that. But I imagine that wouldn't be the case in terms of actual research side of things.
We actually always make fun of the people who work on software, because we make a piece of hardware and then we say, oh, the software, that's the easy part. You just go do it. But in reality, these guys deal with really huge systems in their own right. And they have to build these kits and these toolkits and these algorithms, and they have the same problem jumping from a project to project. It takes a while for them to get back into it too, because there's so much. It's obviously a different thing. Software and hardware are different beasts, but the more and more we work on it, the more you realize that the more you're integrated vertically, the better you can get of the marriage of software and hardware. I mean, that's one of the key successes of some of the big companies in the world, is that they are so nicely integrated vertically, and they create a cohesive experience, which is hard to do when you don't have both of those things. And that's one of the things that more and more of these companies are becoming vertically oriented because of this fact.
What are these software people doing for you exactly? What type of software are they working on?
Well, at Bell Labs, there's machine learning and robotic control and software for the kind of search engines, experiences, building knowledge base and building databases and answering questions that are related to intention rather than specific thing. All the kind of software problems and cloud-based problems that companies like Google and Apple and Amazon are working on. Basically, they're all a company like Nokia is in that business because they are network designers, and we make networks, massive networks, and these massive networks run on really complex software. It's not just we don't just go to a customer and say, well, here's your network. They
Right.
expect a massive amount of software to back that up, especially if you have cloud services that you want to sell to enterprises. You need to have developed all of that, and that's pretty complicated.
Wow. So what software wise in your group, what would you be doing?
Well, for us, we don't write that much software, mostly for controlling our hardware.
That's what I thought. Test systems and stuff?
Yeah, test systems and MATLAB code and maybe some Python code and things like that. We write it just basically for interfacing for our hardware. But if you want something really complicated, we just go to the software guys in Bell Labs, say, listen, we have this hardware, it can do this and this and this. Can you write a software layer for it to take the most out of it? And then they can work with us on that. Got it.
So what's the leading edge stuff you're working on? What's since we last talked 2 years ago, what's changed? And how often does it change? Is it like every 18 months? Like, Moore's law, does it double? Like, does like bandwidth at a higher frequency double or whatever every 18 months? Is there like a Moore's law for like RF?
Yeah, people do talk about the Moore's law for RF as well. So right now, the big thing, the obviously for 5G networks is the use of beamforming phased arrays for communication, right? So people often talk about going beyond the Marconi era, and that's what they say. And Marconi,
and what does that mean exactly?
So Marconi invented basically wireless transmission, right? He did that in late 1800s, and he did it when he was 20. By the way, he built the wireless transmission when he was 20, and then Braun was another physicist, and he invented phased arrays in 1905. And they won collectively the Nobel Prize for Physics in 1909 together for their contribution to telephony. But the idea was that when Marconi did wireless transmission, the reason it was such a success was because it was isotropic radiation. It's the easiest thing to build. You just put an antenna, you put radiation over the air, you cover the atmosphere completely. You don't care if most of that energy wasted and goes into nothing. But if there is a receiver somewhere that can collect enough energy, then it will use that energy to create, a wireless communication. And that is very successful because of its simplicity, and it was fine for frequencies up to a couple of gigahertz, which our entire consumer wireless industry is basically based on that. Over 100 years, we've been doing basically the same thing. Through a direct,
even your Wi-Fi does that, right? It's just radiating out in a sphere. Basically, it doesn't, care.
It doesn't care. It doesn't care, exactly. And this is why. And people basically have been trying to do the same thing in the past 100 years, is to increase the capacity. So how do they do that? Well, they increase capacity by cramming more bits per hertz. So by creating more complicated modulation, that means that you are more efficient in using the frequency bandwidth you have. And then people start doing even more complicated things, embedding information, spatially in like polarization or MIMO. Kind of thing. MIMO was invented at Bell Labs also. But then what's happened is that now we want so much data from a wireless network, and we want to cram so much into space that we no longer can do it at the frequencies we traditionally are using. We cannot do it at 2.4 gigahertz, for example, because there is no spectrum left. So what do we do?
Is there a limit to, like, have we sort of starting to reach the limits of how much information we can cram into a given bandwidth? Are we just like it's like fabricating silicon, we're getting down to 8 nanometers, and it's like eventually we're just hitting that sort of limit?
Yeah, basically that's exactly right. What happens is that if you go beyond a certain amount of complex modulation per hertz, then you either have to get your transmit receive so close to each other to meet the signal to noise ratio requirements, or it's just not going to work.
Yep.
So it all has to do with, can I detect what I'm sending at the end of the day?
So it's a function of distance.
It's a function of distance, complexity, processing power requirements, and many, many things go into it. But we've basically run to a situation where we say, okay, if you want next generation, if you want to go from 4G LTE to 5G, something has to change for the first time in 100 years or so. So people said, okay, well, let's go to higher frequencies. Let's go to millimeter wave frequencies, starting at 30 gigahertz. Let's do 28 gigahertz as one of the desired bands, at least in the United States. So now what happens is, you can no longer do isotropic radiation in a sphere anymore, because the efficiency of being able to transmit and the losses of signals at those frequencies in free space is so much more that you can't just afford transmitting as much as you want over the air and waiting for someone to catch it. Your link budget would be terrible.
Right.
So people said, okay, now we need to actually target the beam at individuals as opposed to just sending it everywhere. And as soon as you start targeting, you get into the phased array problem where you have to beamform electronically so you can track people as they move around. And this is a completely different way of communicating. Now, phased arrays are not new, as I said, invented in 1905. And have been used in the military, SATCOM, satellite communication has been using it. There are actually quite a lot of places that use phased arrays, but not for consumer at the kind of scale that we're talking about here.
Right.
So what we're working on is the next generation of these devices, building phased arrays for telecommunication and for other purposes. For how do you build these in an efficient way, which can eventually find its way maybe even in handsets and in other kind of communication devices. So the last thing that we published in our team was a W-band phased array, which works from 85 gigahertz to 100 gigahertz roughly. And that is a 384 element integrated phased array. And that's the world record right now in terms of its performance and output power and complexity. But that's kind of the latest thing we've built. So it uses 256 transmit antenna elements and 128 receive antenna elements, and it coherently modifies the phase of each antenna to create a beam and point it in any direction that you want electronically.
So are we talking about a flat array which can then go in 180 well, probably not quite 180 degree arc? What sort of shape is the antenna, and what's your radius of your arc that you can beam in?
Yep, absolutely. It's completely flat, and it's really small, because at 90 gigahertz, the wavelength is so small that you can fit 384 elements in the space of about 4 centimeters by 4 centimeters or so.
Wow.
Yeah, it's tiny.
Okay. So does this mean the matching 5G phone has to have a 4 centimeter by 4 centimeter matching array?
No, it's going to be.
How does this?
No. I should say I think it's 4 inches by 4 inches, not 4 centimeters.
Oh, okay.
But yeah, it's larger. But so this is a really power-hungry system, because to generate signals at 90 gigahertz, to create 256 power amplifiers at 90 gigahertz, these things have a horrible efficiency. Yeah, I mean, this efficiency is only in a couple of percentage. So obviously the efficiency of the system in terms of how much DC power consumption it has for the equivalent RF power is not very high. So you wouldn't put 256 elements on your phone, on your handset. I mean, that will this system consumes 80 or 100 watts, so that's not going to work in your
Got it. So what is a phone would have how many elements typically?
So the phone, so the phone situation becomes really complicated, because these things don't go through your hand at all, these signals. So which means that if you hold your phone in your hand, depending on where your hand is and depending on where you're facing, a different part of your phone may be actually exposed to be able to receive any millimeter wave signals to begin with. So handset challenges for putting these devices in is pretty complicated. It's going to have antennas all over the phone, and it has to select which antenna it's using depending on how you're standing and how you're holding the phone. So the handset problem is really hard to solve for 5G. That's why I think initially you would see it perhaps in cars. If I put a 5G on the roof of the car, that's much easier problem to solve than in a person's hand.
Got it. But even then, even if you plaster them all over the phone and your hand's not the issue, your head can be the issue. If you've only got one tower and your head's between the handset and the tower, how do you deal with that?
Oh yeah, that's not going to work because you need mostly line of sight because of the
Right.
beamforming. So one of the other things is that for 5G, for millimeter wave, at least for cell stations, they're going to have to be much more ubiquitous. You're going to have microcells all over
Wow.
the place
Yep.
because otherwise you won't have reception. So 5G has other tricks it plays. It relies on jumping up and down in between frequencies. If you have
Yeah.
absolutely no millimeter wave, it's going to use low band. Otherwise, it's going to use high band. So it can become pretty interesting. And the algorithms to do this itself are under research as well, of course.
Well, I'm just sitting here looking out a window, and I can imagine that if there's not like with like plaster walls and other stuff on either side, and I can imagine if there's not even the glass, does it get through a glass window, for example, if it can't get through your hand?
Well, the glass window is a whole other problem because if you have a modern glass, it's metal coated.
It's
for
metal
thermal.
coated, that's right. Yeah.
And it will have 40 dB attenuation. I mean, it's
Wow.
unusable. Yeah.
It's unusable. So,
Yeah.
so is 5G simply not a solution to actually replace 4G? It doesn't sound. It sounds like it's completely impractical to replace it on a general scale.
Well, it's not as bad in some ways. So people always look for ways to solve it. So take the window, for example. We have ways of getting signals through the window by receiving it on the outside of the window and then retransmitting it back through the window.
Yeah, but then you're solving the problem by having, once again, orders of magnitude more transceivers around the place, right?
Well, your window hopefully isn't moving. So
that's right.
Yeah.
But
once you have it, then you can find if there's let's just say for instance that you have a tower that's outside of your window that has roughly a line of sight, and then you put a receiver on the outside of your window, and then that translates the signal through the window onto your Wi-Fi signal on the inside of your office, let's say. And then I can give you, a gigabit or 10 gigabit per second over the air, which you cannot get right now unless you have fiber. Yeah.
Oh, that's fantastic for a permanent internet connection.
Exactly.
But I can imagine this is absolutely useless for the thing that I was talking about, which is your general mobile phone thing. I can't imagine every single office in there. My one office tower here has hundreds of offices in it. I can't imagine everyone's going to install their own 5G retransmitter just so that everyone can get their mobile phone working.
No, I know. And also, I mean, if you think about it, why would you need a gigabit per second right now in your phone anyway?
Exactly.
Under any circumstance. So there isn't really a very attractive application at the moment that I can see you would want that. Now, of course, if you had it, I'm sure people would find a way to use it in some interesting way. Maybe you would want to have real
I'd love
time.
a 1 gigabit mobile internet connection here in the, that'd be fantastic. But I didn't know anything about this. I thought 5G was going to be some sort of generic replacement for 4G phones, and we'd eventually phase out 4G phones. But that doesn't sound like that's the least bit practical.
No, the 5G, the millimeter wave aspect of 5G on handsets is a problem that's going to be much harder to solve. But 5G in general is much more than what you're going to get on your handset. It has to do with connectivity and replacing fiber and putting essentially fiber over the air, enterprise access. And 5G has another advantage that LTE doesn't have, is that it is extremely low latency, that you don't have that with LTE.
How low latency are we talking about?
I mean, the orders of magnitude less.
Compared to direct fiber. So if I had direct fiber to a tower that's 10 kilometers away, compared to a millimeter wave thing, what's the difference?
So latency through fiber is obviously very good, but latency through 4G LTE is not good at all. So you cannot use 4G LTE in its traditional sense to do real-time control of something over the air.
Yeah,
that would be very hard. But you can imagine scenarios where, let's say, potentially a self-driving car would want real-time control over the network. So how would you use that over the network? In that case, you could use LTE. You could use 5G for more real-time control of devices if it has the low latency millimeter wave built into it.
So it's more of an additional technology for other applications rather than sort of, mobile phones, because everyone's talking about mobile phones going 5G, but it sounds like there's not a huge, as you said, like why would you need a 1 gigabit low latency connection on your phone?
Yeah, I mean, initial deployment of 5G over for your handset will most likely not be millimeter wave. But like I said, there are many aspects of 5G, other low band and other changes to the architecture of the network, which will have impacts to the users.
Yeah.
But if I gave you a gigabit per second access on your phone, perhaps people will find a way to deploy it in maybe augmented reality, virtual reality, real time on devices that you carry around. Yeah, so it's one of those things. You give it to people will find a way to consume it.
Yeah, of course. but it sounds like the biggest application at the moment would be for the internet, so with the telecommunications companies who also provide wireless internet services, like as you said, for an office here, for example, and they don't have fiber connected to the building, and yet they want that huge pipe coming in.
Yeah, you can imagine a company, let's say in the United States, like Verizon, right? Verizon will give you fiber here. And if you want fiber from Verizon and you don't have it in your area, the cost of deploying that is massive, right? But if they can give it to you over the air, they will.
Exactly.
It will be much easier.
Cheaper.
Yeah.
Yeah. Like for I had to get fiber installed to my building just for me. In my old lab, I literally got them to lay a brand new fiber, even though there were 4 other fibers already there. But that's a political thing. It was like, I think it was $20,000 to install that fiber into the building just for me. And the reason they did it is my payments wouldn't have paid for that, but they were hoping to sign up other people in the building, and I helped to actually recruit other people and stuff like that to help fund that. So
this is also true. No, it's true. It's also for Verizon, the cost of deploying the fiber is so huge. It will take forever for them to recover the cost from a single user. So if they can do it wirelessly, they will. So these are some of the lower hanging fruits when it comes to millimeter wave access for the masses. And there's some other interesting aspects of design, but it's a really cool area of research because you're trying to create a new paradigm of communication at the same entry cost that your existing established communication devices have. And that's a really hard thing to do because it's completely different. And so there's a lot of research and innovation that goes into making that happen.
Right. So I'm interested to hear more about the phased array type stuff, about, grating lobes and all sorts of other, things that come into play in terms of, actually directing a beam. And how would you do it for mobile phone when you have, how do you track so many users, and how accurate does the tracking need to be? Say you've got a tower that's it's a kilometer away. How many, how accurate does your tracking beam need to be, and how many people can you track at the same time? And
so they don't really envision. That's why they need microcells. They don't really envision to be able to have this millimeter wave 5G access for people at distances that are a kilometer, maybe a couple hundred meters.
Okay,
maybe.
So it's closer than it.
It's much closer. It would be maybe 100 to 200 meters.
100 to 200 meters. Yeah. Wow. Okay.
Yeah. So it will have to be much closer. But the situation is also a little bit simpler because the idea is that your connection to the tower, your connection to the network is not symmetric. So you're not going to consume as much data as you're transmitting. So you're going to transmit much less out of your phone. So the link budget...
You're talking to a content producer here.
That's true. Most people...
No, most people don't. Yeah.
Most people want real-time data to be sent to them potentially. And so that helps. But the link margin between your phone and the microcell is not symmetric, essentially. It doesn't have to be symmetric. Making it symmetric is really, really difficult. But you can imagine that you have a much higher aperture gain, a much higher gain from the antenna array on the cell than you have on your phone, because it has much higher number of antennas potentially. So you make up that by that difference in some ways.
Right. So can you explain link margin for those who aren't aware?
Yeah, so the link margin refers to how much, in the most simplified way, how much above the absolute minimum noise are you in a link, in any kind of a communication link. That tells you how much data you can potentially send through that channel. It goes back to Shannon, right? Shannon's theory of communication. So if you are X amount of dB, let's say, above the absolute noise of the system, then you can cram a certain amount of information in that. So if your link margin is really, really, really small, means that you can send only very little data over because your receiver won't be able to distinguish the data from the noise. So that's what I was saying originally, that if when a transmitter and a receiver gets really close to each other, it gets better. That's because there's more power from the transmitter that reaches the receiver. So as you go further and further, your link diminishes and the quality of the link diminishes, and you can send less and less data. Eventually the link dies. And a lot of these communication networks are dynamic, meaning that when the link is strong, they send a ton of data. And when the link gets weak, they back off and send simpler and simpler modulation. They send simpler and simpler symbols over the air.
So it changes the encoding based
continuously.
on the noise. Wow.
Yeah.
Okay.
It's adaptive modulation. Yeah, it's continuously changing. Yeah.
Very interesting. How is it? Is it a linear effect in terms of the amount of data versus noise floor, or is it non-linear? How does it?
So it depends on the kind of modulation you have. So, you can have OFDM, which is a one type of modulation, is orthogonal frequency division multiplexing. You can have QAM constellations, which sometimes in some of my videos I have discussed that as well. So if I have only two symbols, a 1 or 0, I'm just putting one bit in one symbol. Now, if I stretch that and encode information in the amplitude, in the strength of the signal, then I have pulse amplitude modulation. So I have levels that I can encode information in. And if I start encoding information in the phase as well as in the amplitude of the signal I'm sending, then I get QAM constellation.
Right.
And then you can keep going. You can then start embedding information in the polarization of the waveform as well. Then you get polarization multiplexing, and it keeps going. Again, you can encode information in the frequency and polarization and phase and amplitude. And it keeps going.
So you can do amplitude, phase, frequency, polarization. Is that the 4, or is there
you can do also MIMO, which is multiple transmit, multiple receiver. Things add up in and many receivers see all the signals, and then they extract additional information from that.
Right.
And you can go even further and start embedding information in the momentum and the direction of the polarization that is rotating. That's more experimental.
I was going to say, can you explain the momentum of the polarization?
Yeah, that's a really weird one. I know.
My brain doesn't instantly process that. Can you explain?
Yeah, it's not something that I have done personally, but it's very new. I saw I forget which company did it, but they have a point-to-point wireless link where they embed information in the velocity of how fast the polarization is spinning as an additional information on top of it. So then, how fast the polarization spins also carries information. It's something along those lines. Don't quote me on that. I'm making a horrible butchering it, but it's something along those lines.
How much extra info can you add into that, and is it worth it, or are they just doing it for kicks?
Well, in a point-to-point link, when you're not obstructed, it may be worth it. Because you don't have any polarization scattering at all, because it's a direct link.
Of course. Yep.
So you might be able to get away with it. People have tried that in fiber as well. Fiber is really amazing. If you look at the innovations in fiber, it's really cool to see how people innovate in different mediums of communication. Through fiber, through the air, through copper. All of these things have unique ways of embedding information in it. So one of the things that Bell Labs invented for twisted pair, right? Twisted pair communication. Yes. Simple idea. Let's say you have a twisted pair. They're differential. They're twisted for obvious reasons, for interference and so on and on. And I can embed really complicated waveforms onto one of these pairs. And then now let's say you have two of them. And what you can do is you can obviously send data to the next one too. But you can use the two in conjunction and embed differential information between the pairs on top of that.
Right.
So now you have two pairs of twisted pairs, but there is 3 channels of communication on it.
So you're talking about common mode modulation?
Exactly. Yeah,
right.
Exactly. Yeah. So that's called the phantom channel, because it's not really there. So people embed, up to 25, 30, even 50% of the capacity of each of those individuals on top of the phantom channel.
Really?
That's how much they want to squeeze data into the channel. That's how precious it is.
Wow. But then if you try and do common mode modulation, common mode interference becomes a problem.
Yeah, that's why
more of a problem.
Exactly. Yeah. That's why the capacity of the phantom channel is so much less than the twisted pair, because the quality of the channel is so much worse. So you cannot put as much data. But it's just that, people are so desperate. And the same thing in fiber, people put information in obviously phase of light, amplitude of light, and then polarization of light. And in fiber is pretty messy because the fiber doesn't maintain polarization. At least the cheap fiber that people use, a single mode fiber, you can buy polarization maintaining fiber, but nobody uses that in large scale. So once you put information on the fiber on the different polarizations, they get mixed up. So the receiver has to receive it all at once and then figure it out afterwards.
Oh, no.
So there's really advanced DSP algorithms that go into figuring out how to unravel the polarization.
So it's actually possible to do that practically, even though it completely muddles it up.
Oh, absolutely. Yeah, the algorithm. And one simple way to think about it is how could they possibly do that is because the channels are completely uncorrelated. So you have complete decorrelated data on the polarizations, essentially. So you can use some of that information. There's some clever algorithms to separate the data once it's all mixed together. And MIMO is even more complicated because you have stuff from all over the place just adding on top of each other in absolute madness. The fact it works is honestly like magic.
even you who works even your basic stuff we consider black magic, and you're saying there's black magic on top of your black magic.
Oh yeah, God, yeah. And on top, I mean, go to the quantum guys, and then that's really the insanity.
That's where your mind
begins.
Explodes.
Yeah. I know. I don't know if you saw it happened recently, the Bose-Einstein condensate experiment they did. I don't know if you read about that.
What one was that? I might have.
So it's another state of matter, right? And if you just read the description of it and then be in awe of what human beings are capable of. I'm going to butcher that because it's not my expertise, but what they do is that they start with a particular gas of some matter, and then they need to cool it. They need to cool it to microkelvin, like 1 e to the minus 6.
Yep.
So they use laser to knock away high thermal particles, the particles that have high thermal energy in them to heat up. They knock this out and then cool it down to a point where the individual particles become quantum tangled. So now the whole this blob of these particles are all tangled together. And then so once they're tangled together, they're kind of locked in a particular way. And then they cut it in half. And then
why not? Because you can.
And then when you cut it in half, any disturbances to these two halves become detectable because they won't match up anymore. Because remember, these are all quantum tangled. Yeah. And then gravitational fields going through them can disturb them. And then you can potentially detect gravitational fields this way. I mean, this is insanity, right? I mean, I'm sure I butchered the hell out of it, but just go and read it. Go and read what human beings can do and just be inspired.
Wow. Because last I heard, Bose-Einstein condensates were like a theoretical thing. I didn't know they were doing practical stuff with them.
Yes, absolutely. This is a new thing. That's what I'm saying. I was just reading about it maybe about a few months ago. And then this goes back to what I think we might have spoken about this before. The dynamic range between people's perspective of the world is so big, right? I mean, you have people who think about, let's do this. And then people who are, let's say, worried about whether homosexual can get married. I mean, just think about how different that is, right? It's almost like it's not the same planet.
There, it's like a caveman versus rocket scientist.
I know, and this is why I think science in general, is much more. You don't have to be a scientist to use people's passion to change your point of view. That's the really incredible thing about it. I mean, just look at what people are doing and what they're worried about and what their aspirations are and what they think is worth spending your time. It's just amazing. It's incredible.
The thought just occurred to me, like back in the, Einstein's era, right? I'm talking, like the 20s, 30s, all that sort of stuff, like early 20th century. It was the thing to actually go for the public to go to these science lectures. They were packed out.
I know.
These were the blockbuster movies of the day, and now people are going to see some stupid blockbuster, mind-numbing blockbuster movie at the theaters. But back in the early 20th century, it was science. They would go to these lecture halls and they'd hear about these latest things, and people were enthralled.
I know.
Is that era ever going to come back, or is maybe a niche thing on with all the science channels on YouTube, for example? But
yeah, I think. So this is, I'm sure that there are many ways to think about this, but there's a couple of things that I have noticed. So yeah, you're right. Especially during the Cold War, for example, in the United States, they did a survey where they asked, I think they were undergraduate college students, I forget. They asked them, would you rather have a brand new car or a PhD?
Yeah.
And like 80%, 75, 80% said they would rather have a PhD, something like that. But the number was amazing, right? And there are political reasons for that. There were issues happening in the Cold War, and the United States wanted to be scientifically. I get all that. This is all granted. The thing that I worry about is that we're at an age where information is free, right? This is pretty much the first time in human history where you have access to the entire collective human knowledge in the palm of your hand. Right? Yep. This is an astonishing outcome of our ingenuity. But at the same time, what you also have in the palm of your hand is an unlimited set of misinformation. So what is the skill you need, right? 30 years ago, you needed the skill to know things. Now you need the skill to know how to put things apart. That's the skill you need. So, but are we teaching that? Are we teaching that?
I've been complaining about that for...
Yeah, exactly. Yeah. I know that you think the same way. But if we don't teach people how to sort through information in an information age, then things get out of control, because then you have no idea how this is going to turn out. And then we see effects of that in the world.
And people are susceptible to more powerful people who want to take advantage of that fact that people don't know how to sort out.
I mean, it becomes so easy, right? And the issue with this is that any piece of information put online, especially in social media is just... So, I mean, we use social media all the time. So, it's one thing we're bashing exactly the thing we're using. But at the same time, it is such a disaster, because every piece of information that shows up is basically, a person's ignorance is just as valuable as a scientist's input, because there's no way to discern them if we don't know how to discern them. And so you get measles, because of vaccination movements and things like that happening in 2019. I mean, the other
issue is that it's amplified in social media, because you only follow and only get recommendations for the things that you're
absolutely
interested
that's a whole
in.
other problem.
Yeah, I know.
Yeah. And they did this experiment because the way these AI algorithms of these social networks are built, they're built to keep your eyes on the site. That's what matters, right? So they want your attention. So what is the best way to keep you, let's say, as a person on YouTube? Let's say I go and you can do this experiment, and people have tried this. Go and type in YouTube a fairly centrist idea. Okay, let's say you type in vegetarianism. Well, I want to be a vegetarian. Okay, so you type that. Tell me about vegetarianism. Okay, so we show you a video. The next one it recommends pushes that idea to one of the extremes, because that's the only way you would watch the next video. And if you don't, if it just showed you another thing, then you would be bored with it. But now, and then if you keep watching videos, 20 videos down the road, you're going to listen to somebody who's saying we should kill anyone who eats meat. Yep. Right? Because that's the natural extension of pushing it. Or the opposite side, where say we should kill the vegetarians instead. Something ridiculous, right? So there is this effect, like you said, from social media also. And how do you combat that? How do you fight that? Well, you have to teach people who use it from very early on of what to watch out for. How do you distinguish information A from information B? I mean, what is true? What do you call something that is true? And if you can't answer that question, which we don't seem to be able to, you have to worry about that.
But it's not just that, because you can put true, incontrovertible data in front of someone and they still won't believe it.
No, that's the other thing. That's a whole other issue, is that people, in order for you to change your mind about something that you fundamentally hold dear, is that you have to make an emotional sacrifice.
Yes.
Because you have to abandon something which you relied on. And that can be difficult and that can be hard. And more importantly, you have connected with other human beings who share your point of view. And now you all of a sudden alone if you let go of that idea. And these are difficult problems. I know we talk about it and we simplify it, but these are complicated things to solve also. Because people build communities around information which may be false ultimately. And whether there is harm in that is important. We should understand if there is harm in that. And for the sake of the exact people we were talking about.
That's far too deep. Should we get back to the technology?
Yeah, sorry, we got distracted.
I can talk about this stuff all day, but it's unfortunate. I know, ironically, it's not what people want to hear.
No, I know.
People listen to this, they want to hear about the technology, but it's so important. I'm with you,
Yeah.
It's
Yeah, so let's go back to the question you asked earlier. You asked about beamforming and phased arrays. And so the idea, like I said, is really simple, but the consequences are really interesting. So it turns out, as I was saying, if you put a bunch of antennas next to each other, and these antennas are spaced at a fraction, 1/4 or so, or half of the wavelength of the antenna that's operating on. And then you connect them all together, and then you change the phase of the signal to each of the antennas in a unique way, in a predictable way, which you can compute. You can constructively and destructively interfere the waves in open space and tilt the beam in a particular direction. So this basically is called electronic beamforming. It's a foundation of how phased arrays work. And you can do this with light as well, because light is an electromagnetic wave. It has phase information exactly the same way. And that's how solid state LiDAR is supposed to be built. Right? That's exactly the same.
I used to work on this with underwater sonar. It works in water as well.
Yeah, absolutely. It's a wave, so it will behave exactly the same way no matter what. And so that's the idea here. But the things become complicated because as you start tilting the beam to the extremes, all the way to the left, to the right, let's say azimuth or elevation steering, once you're to the extreme, then a side lobe appears in the opposite direction that you want to actually be pointing the beam. And that side lobe can get stronger and stronger and become comparable in strength to the beam you're actually transmitting. So now you're pointing a beam at someone else's poor receiver who has nothing to do with you, and you can blind them. And so
and your efficiency also drops as well.
Yes, absolutely. Because you're splitting your power into two areas, and that is actually illegal in a way because you have to have a certain mask. You have to comply. You can't just put energy into someone else's receiver and blind them, and it can cause. So phased array communication therefore can become very complicated just from this basic fact. Now, how do you even find the user you're looking for if things are moving? If you have no connection, there's a ton of algorithm and ingenuity that goes into that.
I immediately jumped to my mind the chicken and egg problem. Let's say you instantly turn on your phone or your receiver, your internet connected 5G box. How does it talk to and tell the tower where it is, or tell the access point where it is? Actually,
that becomes pretty tricky. So there are many ways you can do this. Obviously, let's just say that what is the absolute simplest, dumbest way we would do it? Well, you would have the tower constantly scanning all the empty areas as it is trying to, and then you just listen to that. And once you hear it, then you talk back. But that you can imagine that's horribly inefficient, right? Because
it's not inefficient in a power point of view, is it? Because you're only receiving, you're not transmitting.
No, but it is inefficient in a throughput of the tower because any amount of because if the tower is just pointing at empty space, it's not using that time to be giving data to people.
Could you have a separate antenna, like a tracking antenna that just does that purpose?
You could, if you were willing to double up on the number of devices and components and all that on the tower, you could potentially have a secondary one just for searching, but then that increases the cost of the system. So people do, that's what I was saying originally, is that one aspect of the 5G is that it still has the low band, the low frequency part may still be part of it. So if you turn your device on initially, it may broadcast that it wants to connect at the lower frequency, try to establish some agreement to the tower, and then the tower can then go back to millimeter wave frequencies and connect to it and track it. So there are algorithms in the background to take care of these things. You said that the transmitter had 256 elements. How many did the receiver have? The one that we made for our prototype is a 256 transmit and 128 receive. But a lot of this is at 90 gigahertz. So making individual elements that work both in transmit and receive is difficult because you need a switch to switch between TX and RX. Now that switch is supposed to work at 90 gigahertz in terms of its linearity and noise and its switching speed and all that. So it becomes
just
difficult.
Right.
Yeah. So people who are working at lower frequencies, even nowadays at these frequencies, they make bidirectional elements. So if you have 256 elements, they can either be transmit and receive, and they can jump back and forth in some fashion to do handshaking and transmit receive.
I can understand having all 256 elements to beamform in the transmission state, but what is the advantage in the receiving state to having that many elements if you already know the location of the actual device?
Yeah, so that the advantage is that it would be the equivalent of summing the amount of energy coming from a specific direction. Yeah.
So it's a energy. It's a receiving capture area.
Exactly. Yeah. It increases the aperture, the gain.
It increases the aperture gain. It's like having a bigger dish pointing into space. It receives so it gives you greater sensitivity.
Yeah. Yeah. I mean, the only difference between a beamforming phased array and a dish is that a phased array can be electronically steered, whereas a dish can only be mechanically. That's the only difference, really, fundamentally. Yeah.
Now, all this stuff you're working on, because there's tons of microwave towers. We've got one on top of this building. I can get microwave internet that comes via a dedicated dish pointed on top of my building to the network hub, which is 2 streets away, right? Is 5G still a replacement for those, just because it's much higher bandwidth, even though, you've got 2 dishes, microwave dishes directly pointed at each other, so you don't need the steering, you don't need the electronic steering. Would you still use the 5G technology for that?
So you probably have a backhaul connection, and that connection is probably shared with a bunch of people. It's not just you.
Yes, and everyone in the building can get access via this one satellite dish to which then goes to another building which has a big trunk fiber, going back to the internet.
So if you have a backhaul connection, that's probably already working at some microwave frequency. I don't know, but by looking at the dish, you can roughly estimate the kind of frequencies operating. But it could be K-band, it could be X-band. I'm not sure what frequency it's operating at. But once you have that link, the bandwidth of some of the 5G systems they're proposing is more in some ways, but the flexibility of a direct connection is going to be hard to beat. So if I were to replace your connection with 5G, and you're already getting, let's say, 10 gigabit per second or a gigabit per second through that link, nothing's going to change. The only difference would be that if I change that with a phased array, the tower could talk to multiple of people by jumping back and forth between them.
Right.
As opposed to just a fixed connection.
But then you would have to split up the bandwidth between them, wouldn't you? Or is the throughput the same for as any number of connections?
No, exactly.
In theory.
So let's say that the connection is 10 gigabit per second instantaneous, and you're sharing it with 10 people, then each person gets on average a gigabit per second.
Right. Okay.
Yeah, it will get divided. But a gigabit per second is still pretty high.
Oh, yeah. It's still pretty good.
Yeah. I mean, it depends on how many people divide it, but it's still pretty high. Yeah.
But if you're talking about 5G is really only relevant for like the hundreds of meters, 100, 200 meters tops kind of thing. There's only so many people or so many receivers you're going to have within that physical space anyway. So
yeah, exactly. So that you would be limited. So if you have let's say in a neighborhood and you want to give 20 homes fiber replacement, and these homes don't have fiber, but you want to give them fiber-like speeds, as opposed to digging fiber to their homes, you can put a couple of towers nearby, give them each a little access point, 5G access point, and they can stick it on their window or whatever they do. And then they can get that service, And then a tower might serve, 10 houses, let's say.
Now I'm going to get into the controversial aspect of this. A lot of people are talking about the safety of 5G, and I've got a hilarious. I didn't take a photo of it, but I was at a market early in January while I was on holidays, one of those local markets, and there was this guy there who manufactures what's called orgonite, and it's this weird rock. It's got metal filings and everything in it, and it's supposed to magically protect you. Of course, it's complete bullshit, right? Complete woo-woo, right? It's supposed to protect you from mobile phone radiation and everything. And last year when I went, he had this big sign on his stand there that said it protects you from 3G radiation, 4G radiation. And this year he just added plus 5G. So it protects
you should have told him it's not even deployed.
Yeah, I know, but he's added it. I mean, this guy's Johnny on the spot.
No, he's keeping up. Yeah.
But I've actually had several emails from people saying, hey, what's with this 5G safety thing? Everyone's talking about, is it dangerous? That kind of stuff, because you're talking about the efficiency is really bad, right? Yes. So you've got to, so in terms of the transmission, so you've got to pump in.
Yeah.
Would you want what are we talking, hundreds of watts? We're talking about kilowatts, something like that, like 30 meters away from you.
Well,
would you actually want that?
You can do a simple experiment. Go to Google and type free space path loss calculator, and then put in the frequency and put in the distance and see how much attenuation there is at a particular frequency.
It's a lot.
It's a lot. Okay.
Yeah.
Let's just put it this way. If there is a very high power transmitter and you go and you stick your face against it, then that could be bad for your eyes, right? Because you're absorbing into it. But first of all, you would never get that close to the transmitter. And a transmitter that's that close to you would overwhelm your receiver. So these things will have to be at a certain distance, and the power coming out of these devices will be adjusted to the distance they have to the end user and the distance they want to cover. That's why if you go up and climb a tower that has an LTE transmitter on it and stand in front of it, you will get hurt. But there's nobody standing in front of that tower. The power that's arriving to your phone is tiny.
Yes.
It's insanely tiny.
How we're talking...
we're talking 100 dB attenuation.
Right.
Yeah.
So we're talking...
It's enormous.
Tens of milliwatts? Is that... Or is it down in the microwatt region?
No, it would be in the micro and nanowatt. It's tiny.
Right.
Yeah. If I could give you 10 milliwatt into your phone, it would overwhelm your phone.
Right.
Yeah. It's a lot of power. And these things have obviously attenuation; they can absorb that. But your cell phone gets a really, really small amount of power.
It's a tiny amount.
GPS is like in the minus 140.
Oh yeah,
150.
It's nothing.
It's nothing, right?
So it's down in it's actually embedded in the noise for a reason, so that it's easier to mask. It's harder to mask out. Yeah.
And the thing is that higher frequencies are in some ways actually a bit safer because they don't penetrate your body at all. There is so much skin depth limitation that they dissipate at the surface of your skin, and they may heat up the surface of your skin by some micro degree or something at some distance. So these things aren't really dangerous, but that doesn't mean you cannot make a microwave transmitter that isn't dangerous. You can make one that's dangerous. Your microwave oven is pretty dangerous if you put your head in it, right? So then, of course, it depends on the use case. But the use case that we're talking about, the amount of powers we're talking about being transmitted is tiny, and it has almost no effect on anything. If you're really close to it, but you're never close to it. But the military developed this device this is now many years ago. It's called the active denial system. It's a 90 gigahertz phased array, same frequency we are working on. And it has so much power, and they can target a beam at an individual up to half a mile away and make them feel like they're on fire.
Right.
Okay? Yeah. So 90 gigahertz radiation will be absorbed by the surface of your skin. It will heat up your nerve endings, and your nerve endings will tell you you're on fire, even though you're not.
Right.
But you're only stimulating them. You're fooling them into thinking that. So people, the military uses that for crowd control and so on. It was deployed in Iraq and in a lot of places. Now, that is an enormous amount of power.
Yes.
I don't know what the long-term effect of that is, but That's not how a communication system works.
Yeah, but you wouldn't want to have it done to you, you know?
No. And people have tried. You know, there was a funny clip of a reporter trying to beat it, and he said, "No, I'm convinced I can do it." And he's standing with his microphone, and they're saying, "Okay, we're about to turn it on." And as soon as they turn it on, he just collapses on the floor because he can't take the pain. Right. So the sensation apparently is really weird, really strong. Even the array we made with 256 elements, if you hold your hand in front of it really close by, you can feel a hot spot on your palm.
Wow!
From the radiated power, but that puts out an equivalent isotropic radiation power of a kilowatt. But that's not. Yeah, that's 60 dBm. Yeah.
Yep. So what about, like, let's say I have my 5G router right next to me. You know, like it's literally like, you know, half a meter away from me. Is that going to be an issue?
No, because it's going to put out, you know, in the orders of
watts.
An ERP of a watt. Yeah, I mean, it's not going to, because it's not trying to go very far. It's the
same as the routers at the moment. You can limit them, and I think hundreds of milliwatts is the most they put out or something.
That is not because it's unsafe for you. It's because it will blind other receivers. I mean, you have a exactly. It's not because if you crank it up, you know, your hair is going to start burning. No, that's not the issue, right? The issue has to do with FCC regulations for enabling other people to be able to communicate, especially Wi-Fi frequencies.
Got it. So 5G safety busted.
Yeah, I mean, there's certainly studies need to be done in the long-term effects of high power nearby, but that's not the situation people are going to be.
That's a different thing. Yeah.
I mean, there are so many other things much more dangerous that you should focus on if you're worried about your health, and just not exercising, just the influence of that one
I know.
thing.
Yes.
You know,
orders of magnitude.
Yes, it's much worse. Yeah. But I always tell people that this does not mean that we should not investigate it. But we should investigate it, but we shouldn't also be misinformed about it. You know, there's what we need to understand the problem and not just have fear for the sake of fear.
I'm sure if you searched Facebook for 5G dangers or whatever, you'll be swamped.
Of course.
And it hasn't been deployed yet. You know, I'm sure.
No. I mean, I said, take things like vaccination. I mean, come on, this is a very well established. For crying out loud, the guy who made up the story lost his medical degree. Why are we even talking about this anymore? I mean, he made it up. What else do you want?
It takes a life of its own once it's out there.
Yeah, the issue is because it's combined with other things people know are true. Yeah. It's combined with the greed of pharmaceutical companies. Okay, that is a real thing. That's why misinformation is so easy to spread.
Oh, goodness. Oh, we could go all day.
Yeah, I know. This is one of those things. It's going to be marked as the worst podcast ever made.
The worst episode ever.
The worst episode. Sorry, worst episode. Worst episode. But I mean, these are important things, and you should be able to have a conversation about them. And if you cannot have a conversation, is the only thing we have. What do we have as human beings? Either we converse or we fight each other, right? Yep, there's nothing else to do.
No, that's it. So how long before we get our 5G internet, router?
It shouldn't be so much time in terms of in your home you don't necessarily have to deploy 5G, which is a licensed band for outdoor usage. Say you can use WiGig, 802.11.AD at 60 gigahertz. That technology has been around for more than 10 years now. You can buy a 802.11.AD router right now. It's just most people don't buy it because most people don't need it. I mean, what do you need a wireless connection to anything in your home right now that's more than 500 megabit per second?
No.
No, exactly. And what are you going to use it for, right? The only thing that I have in my house which could benefit from it is my VR headset because it's wired, right? My VR headset uses uncompressed data going through the screens. It needs low latency, it needs all those things.
Exactly, yeah.
That's where you can use WiGig. And there are people obviously doing that, and you can buy devices for that. But that's the only thing that's actually become available that I can actually see myself buying. Otherwise, what am I really going to use 60 gigahertz in my home for?
No, exactly. It's crazy. Even like streaming movies is only like tens of megabits for even 4K.
Yeah, it's like 28 or 32 megabytes per second for Netflix 4K. You don't need that much more. Yeah, exactly. And the compression is so good that it's almost indistinguishable from a raw 4K data. So you don't need it. There are some places, obviously, which it can be. I actually just bought from eBay one of those HDMI wireless extenders where it's got a 60 gigahertz radio on both ends. Actually,
really? Yeah.
Because I wanted to make a video about it on the channel and take it apart. And actually, people should, because that has a phased array in it.
Wow, really?
That's a fully integrated. I mean, this is my company called Cybeam. Cybeam built that 10 years ago. Those poor engineers, they just invented it all, and there was no one to buy this from them.
Oh, no.
I felt so bad. The technology way ahead of its time. Those guys were really, really good 10 years ago, and that's their chip in there.
But how does it know the location? If it's got a phased array, you need to take advantage of that by knowing the location.
Yeah, but the modem searches and finds a link between the transmit and receive when you turn them on. It searches around until they find each other.
Oh, okay. Yeah. So using the phased array receiver, it knows the location of where it is.
Yeah, I mean, they search the transmitter and receiver, the two ends. They look around until they find... And it's funny because if you look at it, sometimes it finds a reflection and not a direct path.
Right, yeah, of course. Yeah, it's bouncing off a wall or a metal surface.
Or something, And it works so well. And, 10 years ago they did this. It's amazing. Yeah, those guys were
And you can buy
amazing.
it for $5 on eBay, can you? Or is it?
Well, it wasn't $5, but I think I paid $200 or something. But I want to show people, a 60 gigahertz radio phase that you can just buy it from eBay. And this poor guy is selling it on eBay.
That'd be fantastic.
Yeah, but so it's some company.
I didn't know that existed. I really didn't.
Yeah, that was actually Cybeam's original product. It was a HDMI extender, and then nobody wanted it because what they were saying to people, okay, you have an HDMI connection from, let's say, your monitor to your laptop. Let's cut that connection into two, plug an HDMI into this, and then plug an HDMI into the monitor, and then separate them. People are like, I don't want to do that.
Right.
So then they just couldn't sell it, which is a shame because it was a beautiful piece of engineering.
Wow, that's fantastic.
Yeah, and they designed a modem that connects to the phased array, does all the beam steering, all the algorithms, everything was in there. They made everything.
So is this a startup company? And what happened to them? They get bought or they fold or?
Cybeam, well, they were a startup at the time. Then they were picked up, I forget by who, and then they were sold to Lattice, and I think Lattice just Lattice just recently, I think, sold them again. I forget. I don't know what happened to them. Yeah, they changed name to Silicon Image after some point.
Oh, okay, Silicon Image. Okay, yep.
Yeah, I don't exactly know the detail of how they did it, but I knew some of the engineers. Some of my friends went to work for that company 10 years ago when I finished my PhD, and and they were smart guys. No surprise that they made this. But anyway, I'll do a video on it then and show people the incredible ingenuity that's gone into it. Yeah.
Oh, awesome. Well, I think our hour's up.
Shahriar? Yeah, I know. Yeah, hopefully the discussions we had going into the other issues, that's not going to be a problem for the listeners.
No,
but I think
it's good. There's
good.
Enough meat here. It's great to hear about this 5G stuff because it's something that your average engineer just has no clue about. It's just in a field which is so far. Even if you're an RF person, right? All this 5G stuff is still like way out of your field, so to speak. Yeah.
I mean, it is. Like I said, it's totally different. That's whole idea of going beyond the Marconi era issue is exactly that. You're trying to build a completely different technology and mass produce it and put it into everybody's hand. And sometimes the applications aren't even completely clear. So it's difficult to do. But the technology from an engineering point of view is fascinating of what goes into it.
It's great. The fact that you can buy something on eBay with a phased array antenna that's just designed to replace your lead is just...
I know, it's crazy, right? It's absolutely, and you could have done that like 10 years ago, right? This product's 10 years old, basically. I mean, 10 years old. Just think about that.
Nuts.
That's nuts. I know. And now people are like building phased arrays all over again. And the Cybeam guys are like, come on. We did this a decade ago.
Lame.
Yeah, it's like, it's lame. You guys are too far back. Yeah, but awesome guys. Yeah, they're very good at what they do.
Thank you very much, Shahriar. It's been fantastic.
Absolutely. And thank you. It's always a pleasure.
You? Everyone knows about the Signal Path, of course.
Oh, well, I'm not sure if everyone knows.
Signal Path YouTube channel, come on.
Yeah. Well, I have actually now almost about 60,000 followers. The issue with my channel is that, it covers some microwave and some more complex topics, and it's not always interesting to every audience. I try to make it interesting, but it's really rewarding because it's all non-for-profit. It's all I'm just trying to give back to the community as much as I can.
Fantastic.
Yeah, I think I may have said that one other time we were talking. I think the most wonderful thing you can do for another human being, aside from loving them, is teaching them. I mean, that's it, right? And if you look at how many hours people watch just my content, I'm a tiny channel. I can't imagine what those numbers must be for you. But you could be a professor, because I teach at Columbia University as an adjunct professor. I teach one course a year. I would have to be a full-time professor for millennium at a time in order to even come close to those hours, to those numbers, right? So it's
exactly
it's
the
really
number
rewarding.
of watch hours.
Yeah. Like, so it's really rewarding.
Like 1 billion hours watched or something. It's
crazy. For me, it's like
stunning.
almost 100 years. Like it's a century.
I know,
a century.
It's
It's crazy. It's a beautiful thing. I think it's so incredibly rewarding to see that. And so this signal path, YouTube channel. Feel free to go check it out and see if you like the content. Like I said, it's for the benefit of people in my small role in giving back to the community.
Excellent. Are you on the Twitters?
Yeah, I have a Twitter account. Yeah, the Signal Path is also on Twitter. I'm actually, that's the only two places I'm at. I'm at I don't have a Facebook account. I have just excellent. Yeah, exactly. It's YouTube and Twitter. I tweet all the episodes that come out, occasional interesting things here and then. I just picked up an X-ray machine. I would love to show you.
Fantastic.
Yeah.
Everyone wants me to get an X-ray machine. It's actually illegal here for me
to
buy an X-ray machine. It's illegal for you to sell one here in Australia or import one without a license. You've got to sell it. If you own an X-ray, say I actually had a license to own an X-ray machine here in Australia, I could not just sell it on eBay. I would have to ensure that the person I sell it to has the required license.
Yeah. Interesting. I don't think it's the same here, obviously, because I just bought this from eBay. But but it's amazing. The pictures that come out of this thing is crazy. Yeah, it's
fantastic. I would love to have one, but it's like I just can't physically get one.
I'll show you in an episode. Hopefully, you can see how it looks.
That'd be great. Well, thank you very much, Shahriar.
Yeah, thank you, Dave. It was a pleasure. Hopefully, we get to chat again sometime in the future.
Cool. Catch you next time.
All right, take care.